Okay, so good morning. Today we are going to look at cryptanalysis of two ciphers, and I think we started with the cryptanalysis of shift cipher last time. I will again recall few things, and then we will go to the actual analysis. Now, this cryptanalysis is the most difficult part of any cipher actually. There are so normally these are based on, as I mentioned, about probabilities and so on, or statistical properties of the English text. So let me first give you some idea uh, about substitution cipher, cryptanalysis of substitution cipher. Now, if you want to do it by hand, it is a very tedious process actually. You have to observe the ciphertext, observe the patterns, and then try to guess and then keep on observing. So it's very tedious process. So normally people write a computer program, right? So I suggest maybe you can write a computer program to actually verify. I think by hand we will not be able to complete the whole cryptanalysis, but at least I'll give you some idea how these things are going on. And second part, then we are going to talk about cryptanalysis of this Vigenere cipher, and then there we are going to use a method known as index of coincidence. Okay, so that is very important. So all probabilistic based. So these two things we are going to do now. Okay, so we are looking at classical cryptography. We talked about substitution cipher. So first of all, this is a substitution cipher, if you remember. Okay, there is a permutation. So you just permute the things. Okay. We talked about affine cipher and Vigenere cipher. Vigenere cipher, as you can see that, what are the important things? M, the what is the size of the keyword? M is important. Then this encryption rule is just we are adding K1, K2, Km, right? So basically, and this key is important. So K1, K2, Km is also important. So if you want to break this crypto system, if somebody can give you K is equal to K1, K2, Km, then you are done, right? You can actually decrypt everything. So we will see that how to guess this M and K both, okay, so that you can decrypt the whole thing. Okay, so normally in both of the cases we are doing the known ciphertext attack, means ciphertext is given to X and we want to decrypt it. Okay, try to find the original plain text. So again, recalling the statistical properties of the English, this table is going to be very important. Okay, so Baker and Piper table. So essentially, these observations, these 5 observations, are heavily used. Like E is having the highest probability, and this is known as second group. So this is first group having only one letter E, the probability 0.120. Second group TAOINSHR, each having probability between this range, right? D and L each having probability around 0.04, and CUMWFGYPB each having probability between 0.015 and 0.028. So they are less occurrence. And then these last group VKJXQZ each having probability less than 0.01. So these things occurs least in the English text. This is a very important observation. So basically, we call this group 1, group 2, group 3, group 4, group 5. There are 5 group formation of the alphabets in any English text, right? And we are also going to use this fact. So 30 most common diagrams are TH, HE, IN, ER. So diagrams means 2 bits, and trigram means 3 bits, right? Which one occurs most, which one occurs less, and so on. These kind of analysis we are going to use. Okay. So for a fine cipher, again I'm recalling a fine cipher. So we had the cipher text. So we just observe that the length is 57, and then we count which alphabet is occurring how many times. We prepare this table, and now you can see that, you know, R was occurring 8 times, which is the highest, right? D is occurring 7 times, E, H, K occurs 5 times, F, S, V occurs 4 times. So we can go back to that statistical properties and match one by one, right? So if R is 8, so that means which is the highest probability? E. So R should be corresponds to E and so on, right? Those kind of analysis we have done. R is E, then we guess D to be the next one, T. So that means encryption rules are like this. Solve the equation and see which one is the legal valid thing, right? I'm just recalling this much we have done. This is still easy, you know, and then finally you are able to decode everything. Now, substitution cipher analysis is a bit tedious. You will observe that it's a lot more work involved. So I'll give you an outline, you know. Doing everything one by one is very difficult, but you know, I'll give you an outline, and maybe you can probably you should I just invite you to go over it again and again to basically decrypt everything, okay? Okay, so first of all, observe that this is our plain text given, sorry, cipher text given. So starting from Y and ending at R, and somebody tells you that this is coming from substitution cipher, you have to decrypt it. So watch it carefully. What we do, we look at again we prepare the frequency for each letters from this observed text, and we can make this table. Now you can see that Z is occurring 20 times, which is the highest. So Z should correspond to E, right? Because E is the highest in the English text. So decryption of Z is E, right? This is first guess, and I think it is very easy guess. Next guesses you will see will be tricky things, okay? Then if you look at again the table, C, D, F, J, M, R, Y, each occurring more than 10 times. I'm again observing the table. Each of these letters, C, D, F, J, M, R, Y occurs more than 10 times. Now, if you remember, in the English, in the statistical properties table, we had E was the top one, group 1, and second group was having this T, A, O, I, N, S, H, R, which is the second group. So this should match to this. I don't know which one to what, but I know that this group should match to this group, right? Okay. So somehow we need to find a further connection between this. At least I'm able to identify, because these are occurring 10 times, so they should correspond to this second group. Group wise, we are able to match. Any question up to this point? Clear? Now the trickiest part. What we do now? We look at diagrams. So we look at the diagram DZ and ZW. So basically, if you look at here, DZ is occurring how many times? I have marked it. So DZ is 1, 2, 3. There is one more actually somewhere. I am unable to find out. I think last time we have done it. So can you find somewhere? First line. Yes, that is there, right? MDZP, right? So DZ is there. Can you see that in the first line? Yeah. So basically, you know, looking at and marking them and trying to do the analysis is a tedious task, right? So you want obviously computer for doing all these things, right? So we observe that DZ is occurring 4 times. So I'm just writing the observations basically, right? DZ and ZW occurs 4 times, NZ and ZU occurs 3 times. Then all these diagrams occurs twice. Okay, so these observations you can make from the table. Look at the diagrams, which one is occurring how many times. Now, ZW occurs 4 times and WZ not at all. WZ is not occurring, you see. So basically that means W occurs less often than any other character. So we guess the next from the table is the decryption of W should be D from the table. Okay, so it's a combination of the observation, right? So that means W should be D. So we are able to guess two of them, right? Z, capital Z is E and W is D. And then we look at the other diagrams. DZ occurs 4 times and ZD twice. So that means we get a set of observations. So DKD could be R, S or T. I don't know which one exactly, but there is a group. Again and again, I am looking at that Baker and Piper table, right? I'm just matching everything from there. Okay. By doing this analysis, we arrive at the, since Z is E and W is D, so then we look at, the other ones. So ZRW occurs near the beginning and RW occurs again later on. So so since R occurs frequently, and and D is and D is a common diagram. So basically that means again we guess that dk of K is N actually. So decryption of K is N. I mean, so I think it's difficult to do it again and again, but at this point you have something because you have observed some text, you substitute in the cipher text, then again do the analysis. So NZ is a common diagram and Zn is not. While again in this observation you arrive at that decryption of N is H and so on. I think so. Again, by looking at the text, I mean the portion of the cipher text like NE dash is missing, NDHE. So you get C is decrypted as A, and this analysis will give you bit further. Then all these English properties, right? So AI occurs more than AO and all those kind of things. So we decrypt that, what is M should be I or O, all kind of things. M is a vowel, right? So vowel should match to one of the vowel I or O, and so on. This kind of analysis, finally, I'm not doing it complete thing, but invite you to do this analysis, right? Finally, you will arrive at something like this. So this is kind of bit tricky thing, right? So what you need, probably 5 cups of coffees to decrypt it. So it is very tedious. Or you write a computer program entirely based on statistical properties of English, right? Observing so many things and so on. So it's always difficult to do it manually, right? So I try to give you an outline, the analysis, how they do it. Anyway, next one is not very difficult. So next we are going to do cryptanalysis of Vigenere cipher. Okay. So Vigenere cipher I just mentioned to you, right? So the key is K is equal to K1, K2, Km, right? So it is a 3-step process. If I have to decrypt this, what I should do is step 1, point M. Okay, point M. And there are 2 methods of finding M. I'm going to describe both of them to you. Second, find key. Once key is you are able to find key, then you can, so that means you can find K is equal to K1, K2, Km. Once key is given, you can decrypt and find the plain text from the interpret text, right? So these 3 things are there. So any idea how do we find M? M is what? If you look at the Vigenere cipher, M is the size of the block, right? The block, so key length is M, right? So basically it is taking M bits and then doing the things, another M bits and doing the things. So that means if you look at the cipher text, so there should be a block of, some sort of pattern we can observe. And that observation is useful. I mean, Kasaki gave that idea, so which I'm going to write it here. So this is the ciphertext from Vigenere cipher. So you can observe that CHR is occurring at so many places. This 1, 2, 3, 4, 5 places at least I can observe, right? So some portion of text. Actually, I should mention the observation first before telling this. This is the observation. 2 identical segments of plain text will be encrypted to the same ciphertext whenever they occur in the plain text. So suppose there is a same text encrypted, giving you the cipher text, and some other place the same text is coming. Like for example, CHR is coming at, so basically what I'm saying that there is a correspondence between plain text and the cipher text, right? They should be at the same distance apart, right? So we are calling that two identical segment of plain text will be encrypted to the same cipher text whenever they occur in a plain text. So whenever if there are delta distance apart in the plain text, same distance will occur in the cipher text as well, right? But that distance will be fixed, right? So that means that delta should be multiple of m, right? Obviously, it will repeat, right? So it should be multiple of m. Conversely, two identical segment of cipher text, if length more than 3, there is a good chance that they correspond to the identical sequence of plain text. This is again an observation. So for example, here you see the CHR is occurring at certain distance, right? So we need to count the distance between the different CHR positions. So that's what we are doing here. Actually, if you see here, this position is 1. Second one is 166 here. You can count, Then 236, 276, and 286. Right. So basically that means if we compute the distance, so 165, 235, 275, and 285. And so normally if you take the GCD, which is 5, so more likely our M is 5. This is one way of finding M. Got it? So by observing the distance of the similar cipher text portion of the, so whole cipher text is given, we are looking at a small portion of the cipher text, and this is occurring at certain distance. Okay, so we are just computing the distance, computing the delta, and actually then taking the GCD. So more likely M is equal to 5 in this text. I will show you now with another method how we can find this M. Okay, first we need to find M, and then we need to find key K. Okay, this is a observation based on, this is the Kasaki method, but there is another method which was given using index of coincidence. I'm going to talk about that method, which is purely based on probabilities. Okay, so the one which I used today, I mean just now, is the Kasaki-Babbage test. Search the ciphertext for pairs of identical sequence of length more than 3, and record distance between the their strategic position, their starting position of two sequences, right? So suppose it is delta 1, delta 2, and so on. Then M divides all of this. So basically M divides the GCD of this, right? So this way we can compute M. So just now we saw that M was 5 by this method. Okay. Now we are going to talk about William Friedman method of 90-20. So this method is known as index of coincidence. Okay, so what we do, we start with x. Suppose x is equal to x1, x2, xn. And IC of x, known as index of coincidence of x, is the probability that two random elements of x are identical. Two random elements of x. X is a vector, x1, x2, xn. What is the probability that two random elements of x are identical? Okay, I am writing it IC of x. Okay. Now, in fact, we can compute this index of coincidence for the English language. Okay, and so there is a fixed number for that. So what we do? So suppose frequency of A, B, C, D, etc. up to Z in X are F0, F1, F2, F25 respectively. The frequency of each letter alphabet thing is some frequency is given, right? Now, two elements of X can be chosen in how many ways? N choose 2 ways, right? The size is N choose 2. Two elements can be chosen in choose 2 ways. And for each I between 0 to 25, there are Fi choose 2 ways of choosing both the elements to be I. Right? Correct? So a simple calculation. So index of coincidence will be, so index of coincidence of X will be this summation divided by N choose 2. Right? So I can compute this value is Fi minus 1 divided by N minus 1 and over that summation. So this is the general formula, and of course you can apply to any language. I am not sure about other languages, Indian languages, but I think at least for English, we know what is this value, IC of x. So if you can find out this for other languages, that will be really nice. Okay, so let us look at this. So if x is a string of English language text, okay, and if the expected probability of occurrence of the letters A to Z is P0, P1, P25 respectively, index of coincidence is summation pi square, and in fact this remains fixed, turns out to be 0.065. This is a very magical number which you need to remember for the English alphabet. Index of coincidence of English language is 0.065. Okay, IC of x. So this is the observation, right? I mean, so if x is, so the good thing is that if x is a cipher text, then also this probability will remain unchanged, right? So this probability will remain unchanged. So basically, this IC of x is a beautiful magical thing which we can use to compute the M and key both. So I'm going to do now some. So remember, in the substitution cipher, we looked at diagrams, trigrams, and so on. Essentially, the idea we are generalizing in terms of substrings, basically. So what is there? If y is equal to y1 by 2, yn is a cipher text, and there are m substrings of y as y1, y2, ym. M substrings I am taking. So say y1 is y1 ym plus 1, y2 m plus 1, and so on. Y2 is y2 ym plus 2, and so on. Ym is ym, y2m, y3m, and so on. So this array of m cross n by n kind of thing, right? M cross n by m. These are rows are substrings of yi, right? Substrings, right? We have created. Now, if m is a keyword length, index of coincidence of yi turns out to be 0.065, right? And if it is not, this value is 0.038. Okay, so this is an observation which is an important observation. So basically, there are two kind of things: 0.065 and 0.038. Now, this is a very important thing. Now we look at the ciphertext, and we can use these formulas actually. So for m is equal to 1, so now we are looking at this ciphertext which we have shown here, and I can compute index of coincidence for substrings here. Okay, for m is equal to 1, 2, 3, and like this, you see. So you see that for m is equal to 1, IC is 0.045, m is equal to 2, this turns out to be 0.046 and 0.041, and so on. For m is equal to 5, this turns out to be 0.063, and so on. So now clearly you see that this one is close to 0.065, right? So that means our m is 5. Okay, because which one gives you index of coincidence close to 0.065, right? I can compute from the ciphertext. So this is not going to change. So that means m should be 5. Okay, we are trying different m, right? M is equal to 1, 2, 3, 4, 5. Whenever we get index of coincidence close to 0.065, we are done, right? That means most likely m is equal to 5. Now the question is how to find this key. K is equal to K1, K2, Km. So m we have found, and as I mentioned, there are two methods for finding m from the ciphertext. One method is observation, right? Compute the distance, right? And then take the GCD and so on and so forth, right? And then you can find m. The other method is basically just compute the index of coincidence. Okay. Now we need to do some more probabilistic framework to compute key, K. So for I between 1 to m, suppose F0, F1, F2, F25 are frequencies of the alphabets A, B, C, Z up to Z in the string yi, and let n prime, which is n by m, is length of yi. So remember we divided into n by m size, right? So n by m is, suppose we call it n prime. It's the length of yi. So probability distribution of 26 letters in yi will be f0 divided by n1, n prime, f1 divided by n prime, and so on, f25 divided by n prime. Okay. Now, shift ki, so shifted probability distribution we can compute fki divided by n prime and so on. Okay, everything is modulo 26. Now this will be close, to p0, p1, p25. So basically, if you compute capital Mg, this u number for g between 0 to 25, we compute summation I is equal to 0 to 25 pi fi plus g divided by n prime. I can give you some values of here Mg. So if g is equal to ki, Mg is equivalent to 0.065. If g is not equal to ki, Mg is smaller than 0.065, right? So since m is equal to 5, small m is equal to 5, Mg, we can actually compute Mg. Let me show you for the ciphertext. This is the value here. So for this ciphertext, we can compute these values. Now, how do we find key? Now, if we start from first one, so this is for each Mg of yi when I is equal to 1. So you see, these values are computed for the ciphertext. Of course, you need to write a computer program. 0 is 0.035, 1 is 0.031, 2 is 0.036. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and this is 9 actually. So 0.061 is 9. So the first entry K1 is 9 because 0.601 is close to 0.065. 0.065, right? Index of coincidence 0.065, right? So this is close to this. Then go to the second round, I is equal to 2. You can see that among all the values, observed values, 0.069 is close to 0.065. So the second one is 0. Indexing we are doing from 0, right? So this is 0. So second, so K1 is 9, K2 is 0. Third one, again we compute. Now you can see that 0.066 is close to 0.065. So you compute 1, 2, 3. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this number is 13. So that's our 13. Similarly, 4 and 19. So that's how we get key K. You saw how difficult it is? Cryptanalysis is always difficult, right? I mean, so many things trying to use probability business and right. But still people are able to find, decrypt it, right? They are able to find solutions somehow. So here also, so 0.060 and 0.072 and so on. So basically you get key. And so once you have the key, you can get the whole thing plain text, right? So I suggest the best way to understand these two substitution ciphers is very, very tedious because you look at all diagrams, and so on and so forth and do all analysis. But people still have written programs. You can find MATLAB scripts actually for doing these things. If you are very enthusiastic and you have got some time free from competitive programming, you can try to implement one or two such things and then you will observe, right? So that is the best thing. But anyway, so cryptanalysis of Hill cipher is fairly straightforward. I leave it. I'm not going to do it. What they do, it is the ciphertext and the plain text both are given to you, and you try to find key, that matrix. Okay, that is the key idea here. So cryptanalysis of Hill cipher we are not going to do, and this is also we are not doing. The first course we don't do this LFSR stream cipher. These are tricky things. So these two things we are leaving. So essentially, in the whole classical cryptography thing, these two schemes were the most difficult one. Rest of things are fairly straightforward, right? This substitution cipher and the Vigenere cipher, right? So cryptanalysis of these two things are important. So index of coincidence is something which is still not very difficult, but the substitution cipher is very difficult. It solve a lot of manual things, right? Keep on observing, guess something, and then go back to the plain text and so on and so forth. People normally don't cover it, but at least I wanted to show you the difficulty actually in getting the stuff, So that is fine. So I think that's all about this cryptanalysis. So by the way, so I think as I mentioned, so maybe you can look at Indian languages and can you find out these statistical properties? Did you try it? Why should we use English? We can use Sanskrit or Hindi or Gujarati or whatever and try to make a crypto system. Somebody can take that project if it is not done right and develop this cryptanalysis system. In the next class, we are going to do Shannon probability idea, Shannon theory, which is very, very important. Uh, I think, yeah, so that's really interesting. So from now onwards, so I think we have finished chapter 2 in your book, if you're reading. Now we'll go to chapter 3. Okay, so that's all for today. By the way, tomorrow there is a class at 11 o'clock, right? So in February we have, I'm away for 2 days. So basically 2 classes will not be there. But tomorrow and next Saturday, 11 o'clock, same room.